Afternoon, everyone. All right, so my plan for today is that we wrap this conditional text generation approach using RNNs. Today we are going to introduce one important mechanism to this process. And then we are going to talk about midterm. And I will open the floor for questions related to anything we have covered in this course up to today. And if you don't have questions, I will kind of just go over what we have covered so far, and then maybe as I am going through it, we will also, new questions will emerge. So yeah, use today as an opportunity to, clarify anything there where you feel shaky. And then, as I said, the logistics of the midterm, we are going to talk today after we cover this attention business. Okay, so last time we talked about neural machine translation, which is our example of conditional text generation, right? Like type of text generation, type of next token prediction, where we condition on some preceding sequence of tokens. In machine translation, that's giving some source sequence in one language. We are interested in generating a sequence in target language. And my examples were all in English and Croatian. And our approach to this was to use a sequence-to-sequence approach, which is a general approach typically used in the neural world to denote that you are generating from one sequence to another. And sequence-to-sequence approaches often, not always, we'll see later in the course, realized through the encoder-decoder neural architecture, which consists of two pieces. One is the encoder piece, which encodes the sequence, source sequence in a vector of a fixed size. And then decoder part takes that encoded representation of the source sequence and decodes it, meaning it generates token by token. An encoder-decoder architecture can be realized by many other neural architecture. In our case, we have been using recurrent neural networks. But as soon as we come from the full break, we are going to start talking about transformer architecture, which will be what we actually use to do these applications like neural machine translation. But these bits and pieces that we have learned through RNNs are going to be useful when we come to transformer. Okay, so just to recap, to check that I mentioned everything important here, we have encoding of a source sequence. In the last hidden representation we get for the source sequence at its last token will be what we deem to be representation of the entire source sequence. Here, keep in mind that we have learned other ways of displaying words. So here we have argmax, which now we know we call greedy decoding, but here we have other options. Also here we are using in this illustration teacher forcing because, we do not use teacher forcing because we are always using the word that actually is generated as the input at the next token position. What else do we have here? Yeah, that's basically encoder encodes the source, decoder decodes this target sequence. And the issue here is that it turns out that this idea that the last hidden representation at the last token of a source sequence should encode all the useful features of that source sequence is actually too ambitious and too optimistic. What happens in the practice is that this single vector of whatever dimensionality we have chosen as a hyperparameter cannot cram all this information and be useful at every decoding step appropriately. So it is a bottleneck. It is too ambitious of a goal to deem that the single vector will be sufficient. it needs to encode all this information. And now you can imagine if we try to encode really long sequence, how much information you will need to capture in that single vector. And then another piece of, another issue here is that at the different decoding step, different parts of the source sequence are relevant. Remember when I was telling you how initial approaches to machine translation were trying to learn word alignments, right? Like knowing that this word means this word in another language, and you're trying to learn these alignments and then predict which word in a target language will be aligned with the word in a source sequence. So depending on where you are at the decoding time, a different part of your source sequence might be important for that decoding time step. So there is also some notion of this kind of like information from the source sequence being dynamic in some way. And this brings us to attention. So attention is a mechanism that's going to help us address this bottleneck problem that we are trying to cram all the information from the source sequence just in a single vector. It is proposed in 2015. You know how I keep bringing those tests of time of words papers from NeurIPS? Well, NeurIPS is going to happen in December this year, so we don't know yet which paper will get this award, but I would not be surprised if this paper receives it. And the core idea of attention is that at each decoding step, so each time we are trying to predict what the next token could be, we are going to use some connection to encoder and give a chance to look at the source sequence again and kind of see, is something from the source sequence more important for this decoding step than something else? So we are bringing this almost like a direct connection to the source sequence or the encoder before we decide what the next word is going to be. So now I'm going to visualize this, how this works, and then I'm going to write math on the board. So there is going to be two opportunities to understand this bit. So here, don't focus on the symbols. Try to understand what I'm visualizing, and then we're going to write a detailed math later. Okay, so we start from the first decoder step. So here we are, remember in our target sequence is going to start with that special BOS or a start token, and we need to predict what the next token is. And remember, we have produced some hidden representation of that first token in the target sequence, namely here start of the BOS, which is conditioned on the representation of the source sequence, which we said is the last hidden representation of the last token of the source sequence. And now, usually, without attention, we would just introduce our output layer, namely we would multiply the hidden representation with the weight matrix that would give us logits over the vocabulary. We would apply softmax, get probabilities, and sample from the probability distribution. But here we are going to do something extra. We are going to take the hidden representation of the current decoding step, and at every source hidden representation, we are going to make a dot product. Basically, they say how similar is the vector, the hidden vector at the source sequence position 1 to the last one, to this current representation at the decoding step. So we are doing dot product not once, but with every single source hidden representation. So we do multiple of these dot products. I hope that's clear. So here in this visualization, we have 4 hidden representation in a source sequence because we had 4 tokens in the source sequence. And given our current representation at the decoding step, our current decoding step, we are making these dot products and we get 4 values, right? Like dot product will give us a single scalar, but because we did it 4 times, we are going to get 4 values. Now, basically these scores tell me how similar these vectors are. And throughout this course, that similarity has had some notion of importance to us, right? Like we kind of conflate these two things. They aren't quite exactly the same things, but to us, very often high dot product means high importance between two things. Now, as always, I'm a little bit unhappy that how do I interpret this course? Are they high? Are they low? It's a little bit hard. What can help me here to make the interpretation easier? What could I do? Yes, please.
Equality values between 0 and 1 data softmax.
Exactly, right? Like my softmax is my tool in the toolbox that helps me squash the values. And then every time I do this, no matter which instance I'm looking at, I have range, right? And I can tell the range is between 0 and 1. And 0 means very low and 1 means really high. Previously, I could have gone to dot products that are 100,000, 1, 35 million, you know, like they're so varied because dot product is not bounded. So I can get really high values and it's really hard to say how high is high enough. So I'm going to put all these dot products in a vector. So we'll get a vector of size 4. In this example, I'm going to apply softmax and I'm going to get again a vector of size 4, where now values in that vector will be between 0 and 1, and the entirety of the vector will sum to 1. So I get something like a probability distribution over the source sequence, right? And that's sweet. It kind of tells me which tokens in the source sequence are more or less important for a given token at a given decoding step. So again, I would really welcome you to try to think of machine translation. It's a nice example to visualize importance. I hope you speak 2 languages. And if you do, or even if you dabble in one and can imagine translation between these 2 languages, you do know that there will be some word alignment, right? Like you will simply have a word in one language that means something in another one. And this is a situation where with this attention mechanism, you should get really high attention score for words that are really aligned and less attention on it. I hope that this is helpful. It's unfortunately, we don't all speak 2 same languages, so I can't make this analogy super clear. Okay, so now that we got these important scores over the source sequence tokens, we are going to make a new representation of the entire source sequence, where we are going to take information from each source sequence token's hidden representation based on its importance. So if the first, like here, if the first word was really important in the first decoding step, which it usually is, then we want to take a lot of information from the hidden representation of the first token and less from the others. And the way we are going to do that is by simply taking a weighted sum of the hidden representations in the source sequence. Again, I'm going to write the math from the beginning, so don't worry if this doesn't click just yet. But you can think about, now I have certain value, certain weight associated with each source token. So let's say the first one is 0.9 and so on. Then I'm going to take the representation of each token and multiply it by that weight. So I take 0.9 times the entire hidden representation of the first token plus, I don't know, 0.05 times the hidden representation of the next token and so on. So that will give you a vector, a single vector of the same size as the hidden dimension, because you are just summing the hidden representation, but they are going to be weighted by their importance for that decoding step. And now we are not going to discard this last representation that should encode the entire sequence. Rather, this new representation, which is contextualized with respect to the decoding step we are at right now, we are going to concatenate it with that representation we used before, which is the hidden representation of the last token in the source sequence. Basically, what you're doing here is you're like, all right, I need to decode what the next word is, and I kind of want to have a global view of the entire source sequence, and that's that hidden representation you have used previously before attention. So you keep it, you don't want to discard it, it's valuable. At the same time, you know that every decoding step can have some bias towards different source tokens. And this is what you get out of the attention mechanism. So you have almost like a local view of the source sequence. And you use both of these informations by concatenating this vector representation. And then instead of doing our output layer based on only the ST, which is the hidden representation of the last source token, you don't do it just based on that, but you make it based on all of this, which makes that you need to define weight matrix that's larger than it originally was, but everything else stays the same. Okay, so we do that, and remember, we do this for every single decoding step. So you can see how here, if you look at the attention distribution, it's changing, right? So now suddenly some other token in the source sequence is more important for this decoding step, and so on. And you just keep on doing that, okay? So this is a visualization, but we're going to write the math down here. Are there any questions that I can resolve immediately before we start writing math? Yeah.
So is the idea of this attention step that instead of having all of the encoded vectors, generate equal importance to the decoder step, some of them are going to be weighted higher than the others, and that's going to mean, is that going to mean that there's less overall information that needs to be stored, which helps solve the bottleneck problem?
Well, you're using, remember what I said, you're still using the previous hidden representation of the source. So you're not discarding that. So you're adding more rather than less. But that hidden representation previously had everything kind of mixed together, and it's really hard for the neural network to then decompose where the information came from, and it's just too embedded in that single vector. So you give it another vector where it has information about the source specialized for that decoding step.
Okay.
And both is kind of useful.
Okay, so that attention output vector is what we're giving to the decoder rather than what we had previously.
Let's go over the math, and maybe that will answer your question. I think it's a bit hard to answer it now. Yeah.
Would this method take more time than the knife sequence to sequence because we're calculating more controls?
For sure, it's going to take more time. I don't know how much more time are we speaking here, but definitely more. Yeah, you have more computations, you have a larger outer layer. There are multiple pieces of things you need to consider here, and especially when we are doing this one by one, like at the inference time, then you need to calculate all of this to be able to go to the set. Yeah. But then when we start to talk about attention mechanism in transformer, then I will teach you how it's quadratic in the input length, and that poses huge issues because I'm going to work my models that can process entirety of books, and I have 100K squared. That's pretty complex, yeah. So wait for that. We are going to definitely talk about that in this course. Right, so please let me know. I'll try to write larger while not taking the entirety of the board and then needing to delete all the time. And let me know if you don't see something. So we have our training data. I'm going to repeat the sequence-to-sequence approach we have seen last time. So we have our source sequence, and we are going to have parallel examples. So target 1, target K, ith example, for I to 1 to M. So just to read this out loud, our corpus here is a parallel corpus, meaning we have two aligned sequences, source sequence and target sequence. I'm iterating order here from I to n, meaning we have n such pairs. And the length of the source sequence is L, while the length of the source sequence is K. They don't need to be the same, right? So with my RNN approach, I have defined that my HS0 is going to be a zero vector. And for the sake of simplicity today, I'm going to, actually no, I'm going to still keep the layer, right? Like here you have visualization just for the single layer, but I think it's helpful to see two layers. So here, regardless of which layer I'm producing this representation in, I'm going to initialize this with the zero vector, whereas my HD0 is initialized with what? Does anyone dare to say? Want to give it a try?
The representation class.
Yeah, right. So it's going to be HS
of 4 in this case, but
yeah, here is going to be L, right?
Yeah.
Yeah. So L of the layer. Okay. And then I have equations that produce hidden representation in a source orthograph, given in which layer we are. So everything is wrapped in a ReLU. That's our nonlinearity. I had two weight matrices for encoder in each layer, W1, and then W1 was multiplied our history, which was HSI minus 1 of in a given layer. And then I had another weight matrix, which was W2 of encoder in a given layer. And here we have HSI, but in a previous layer, right? So let's go over this one more time. So I have these two weight matrices, and notice how I'm using the same weight matrix for W1 and W2 in encoder for every single token in the source. And in this sense, they are tied or shared because we are applying the same one at every source position. I have one which is representing my history. See here we have I minus 1. We are deeming that the previous token's hidden representation captures the entirety of the history, which is in itself can be also problematic. And here we have a layer minus 1 because we are taking current representation of that source token, I, and we are trying to change it again, right? So the representation we had previously is the one we currently have. And we need to just assume that HSI in layer 0 is the embedding of the word sort of the token SI. Okay, and similarly we have for the target token, right? So we have ReLU of W1, but now decoder. So the weights of the encoder and decoder aren't shared, right? So although I'm trying to kind of do the same thing, represent the history, represent the current decoding token, I'm doing that with different set of matrices. Weights also aren't shared across layers, right? That's why we have additional layers, so it has power to do something extra. But the same thing, HDI minus 1 in a given layer, plus W2, but now decoder in the layer, HDI in layer, but the previous one. And same thing here, we have HDI in a 0 layer is the embedding of DI. Okay, so this is basically a recap of what we talked about last time. There isn't anything new here, it's just compactly written. And let me put this at the top. There was a question of whether I will ask you equations in the midterm. I would not ask you to write me equation and learn it by heart, but depends how you like to learn. You know, you might find this conceptually easiest to understand, and you might put it in your cheat notes, right? So I like to think in a mathy way just because of my background. So for me, that might be a helpful way to memorize or, you know, refer to the RNN. You might write it differently. You might visualize RNN. So I don't know whether it would be helpful for you to write an equation in the sheet you can bring, but I will not ask you, hey, define RNN and write the equations, if that's hopefully clear. So all the questions will be multiple choice questions. All righty, so let's go into the attention mechanism now. Okay, so as I said, attention works at every decoder step. Now I will do the visualization again. So at every decoder step, we are applying attention mechanism. So imagine we have HTJ in a given layer. I'm going to, for the simplicity, start to, instead of spelling out layer, write L, which is overloading L with the sequence length. So hopefully that doesn't confuse you too much. So for every decoder step, we are going to calculate these attention scores. So I'm going to calculate attention score for every single token in my source sequence. So we have IA, oh my God. Letters in Croatian are completely different, so my spelling of these things is just a disaster. But AI means attention score for the source token I. And here I'm just going to keep J because I'm currently at the J position in my decoding step. So imagine here I'm at 1, 2, 3, 4, 5. My J would be 5, but then I goes from 1, 2, 3 to 4. Okay. So this is iterating over source sequences, and I will do that in a given layer. So I will have HDJ dot product with HSI. Okay, I'm going to ignore this layer business because it's just distracting me with this people. Okay, so here we have for a hidden representation at the J decoding step, I am going to look at the attention score for every source token. So for every I element of 1 to L, which is the length of the source sequence. I'm going to do that. And then I'm going to put these into a vector. So I'm going to have I1J to all the way ILJ. And I'm going to produce this probabilities distribution. Therefore, I'm going to have a softmax of this vector. So it's going to be element of RL. Okay, so I have produced that probability distribution. Now I want to produce a contextualized representation of the source sequence relative to the J position in my decoding step, in my decoder. So it's going to be CJ is going to be a sum of I going from, let me just check it out, 1 to L, so over all of the source tokens. I'm going to take the weight of a given source token, which is ith position in my softmax vector, right, I, times the hidden representation of the corresponding source sequence, which is HSI. And finally, I'm going to make a new representation in my decoder step, DJ, which is going to be concatenation of my original representation of the source, which is defined through the hidden representation of the last token in the source. So here I'm taking HSL like I did before, and I'm concatenating it with this new representation CJ. So if I started with d-dimensional vector, I'm going to still produce a d-dimensional vector, and this is going to be element of 2D. This is concat. Okay. And now I'm going to do my standard operations, produce logits, probabilities, and then sample, all based on this new HTJ tilde. Are there any questions about this or any mistakes I could easily make with all of this? Yeah, please.
What's that final logits prob sample? Like what are we computing the logits on? And then the probs on the sample?
Mm-hmm. Yeah.
Is it on that HTJ tilde?
Yeah, exactly. Yeah. So this should now be kind of intuitive. In every part of any kind of model we have produced, in this course, we have tried to produce a representation of the input. And once we have made enough transformation, we said, all right, now comes our output layer, right? So we have done all of this to produce a new representation of the current decoding step, meaning all of the tokens we have decoded plus the source sequence. And now it's time to actually predict the next token, right? And this is where the output layer comes. It's actually composed of multiple layers, but we can refer to it like one big output layer, or output block would be more precise. Yes, please.
It's like the reference HTJ on the first line.
Yeah.
Like we find it.
There's a little tilde.
Oh, yeah.
To indicate that it's a new.
Yeah. Is this clear? I just made up a new symbol to say this is a new representation of the decoding step J.
And so, where is HTJ coming from, and where is it HTJ tilde like going to?
Okay, so HTJ is coming from the same, RNN sequence to sequence approach I have described here, right? So we have created HTJ in, let's say, second layer. And now that we have produced it in that second layer, we are going to do this sequence of operations, and we are going to get a new representation. Oh, I see what you mean. Like this is a representation of the input, right? Like we have source sequence and contextualized source sequence. So somewhere here, we should concatenate it, and I know where I made the mistake, here. So it should come here. So the current representation in the decoding step, because we are doing this recursively updating these representations, has, in theory, all the information up to that point. So all the sequence source sequence token and all the generated tokens up to the position J. And now we're just additionally enriching it with this contextualized representation of the source sequence, and that's where we go into the logics.
Okay, so we have a separate matrix that takes the HTJ tilde and predicts which output token.
Yeah, yeah. And by separate, there's only one. Like one that's going to do the prediction. We don't have two of those. Let me just double check this is correct. Now I'm doubting myself as well. Yep. Yeah, so sorry guys, this is a different notation on these slides. These aren't my slides, but just wanted to double check that the this attention output, meaning this contextualized representation of the source and decoder hidden state are concatenated. So this is correct. So there was a mistake here. Thanks for pointing that out. Yeah.
You previously got rid of the layer notation for this attention. Do we still have to compute this this new hidden representation for every layer of our network?
Yeah, that's a, for me, question of like modeling choice. Nothing prevents you from doing that at every layer. So you could be doing that, and then instead of giving this to the logits, you would give this to the next layer, right? But I don't remember exactly how we used it here in the original sequence. The way it's visualized, it's like we have one layer and there is an output layer which we enrich with this. In theory, nothing stops you from that, except that everything becomes more parameters, more complex.
Right.
So you're always trading the, remember, complexity can lead to overfitting, right? So I can see benefit. Why would you do this at every layer? It would just enrich your representation and makes everything just more informative. But you are then producing twice as big weight matrices. So then you are risking overfitting. Yeah.
So then, if we don't need to do this on every layer, is there a specific layer that we would want to do it? You know, based off of the fact that we have multiple different hidden representations for the source and the target for multiple layers.
Yeah.
In the original encoder-decoder architecture.
So what do you think? Which one is special?
First one?
To me, it would be the last one, right? But this is, again, something we can disagree on. To me, it would be the last one because this is the way I would think about it. I want to produce the hidden representation of the decoder right now. But when I want to produce new word, I also want to remind my model about what is there in the input sequence. So you can consider this very transformed representation of everything we have seen so far, together with some like connection to the input, and make its final decision based on both pieces of information. But I can see like also thinking, okay, maybe at the beginning we need to see what's up in the input relative to the decoding step and then take it from there. So neither you or I are necessarily wrong here, but my intuition is to say you should do it at last.
Okay.
Yeah. Again, bunch of modeling choices that don't come with predefined answer, right? Because this is all modeling choice that you can try out, have a different run of your architecture, and see what happens on the development set. Yeah.
Okay.
Yeah.
So this discussion confused me a little bit. Okay. Can you just explain why we're doing HTLG tilde once again?
Everything again?
No, just the last one. Why we're taking that for each layer?
For each layer. In general, this is information, right? So HTJ is information. It tells you features of everything you have seen so far, including source sequence and every decoded token up to the token position J. So that's one collection of information. Here we have another collection of information, which is what is important in the source sequence giving the input sequence. So it's another set of information. So both are valuable in different ways. And why would you then maybe consider using them at different layers? Well, these representation from different layers themselves contain different informations, right? So your distribution over the source sequences make it different depending on which hidden representation from which layer you right. It can happen, and this is why depth is important in neural networks. I told you, more you transform, more things become separate. So it can happen that only at the third layer of your neural network, you learn something useful. And this is the only point where, from that point onwards, maybe you can capture meaningful distributions. On the other hand, it can happen that information is maybe learned hierarchically. So you have learned some lower level language features in lower layer and more complicated at top layer. So these distributions can all be meaningful, but relative to different features. So you can say on a surface form, this feature, these tokens are similar, therefore their importance is similar. But maybe at the higher level, your model learns something intricate and it's like, actually, I don't think they are so important relevant to this phenomenon. And you notice how I'm vague? I'm vague because everything is learned through the data, and I can't tell you the first layer learns this, second layer will learn this stuff, and so on. So sometimes you need to just give a lot of opportunity to your model and for it to learn. And then later you do what you call ablations. You made the most complicated version of your model, and then you strip bits and pieces and you see what was actually necessary. And you leave the smallest architecture. So you're always juggling between, everything is like black boxy, but it can do a lot if I just give it opportunity. Yeah, and then later efficiency, you strip away things you don't. Yeah. Yeah.
In different languages, different words, you have different meanings. So like, the meaning of one word might be 2 words in another language.
Yeah.
So how do we decide the target sequence then? Because you might have 2 representations for the same set.
Yeah. So basically, in your training data, it's not important because you observe the sequence length and you can pad everything that appears, right? Like your my only pre-processing advice would be if you have too few sequences that are extremely long, there are outliers, throw them trash, and will just cause you problems. For inference time, though, you're right. Like, when do you stop? Right? Is a great question. And here, it's important to add that end of sequence token. And another important thing is to not set up the variable, which determines how many decoding steps you're going to do, to be too little. Okay. If it's too little, what happens? You don't hit the model generating end of sequence token, and your output is truncated and ungrammatical, right? If you put something ridiculously long for the number of decoding steps, nothing wrong will happen. Your model will learn to generate end of sequence token, end of sequence token, end of sequence token. But then you are waiting that we hit that very high number we set to end the fourth one. So basically, what you would do is you would observe, okay, my maximum sequence of my training data, or my 98th percentile was, I don't know, 30,150. That's a reasonable, a little bit higher number of decoding steps to set. Yeah. Okay, let me tell a few more things about attention. So it's an incredible, important concept. It solves this bottleneck problem that we have talked about, where we cram too much information in a single vector and our model can't really make sense of it to the extent we want. It has significantly improved the neural machine translation performance, and therefore that was the task at the time that everyone was very excited about, together with image classification. So gaining really big improvements there without manual intervention, meaning your linguist or translator telling you which words are actually aligned and bringing those inductive biases in your architecture. It helps with the vanishing gradient problem, which is the problem where your gradients, because you multiply them through time due to the chain rule going all the way from the loss at the generated token all the way to the first source token. If you multiply them and they are all too small, you will get a gradient that's very small, and your optimization algorithm won't change your weights. And it does provide some interpretability. So here you have heat maps. Unfortunately, they're a bit small, but basically at the top, you have a sentence in your source language. Vertically, you have a sentence in the target language. And now, because we have learned for every target token that has been generated, you have these attention scores, right? You can visualize them and you get these heat maps. So they look like, lens into how the model thinks these words are aligned, which is nice, but I think researchers got a little bit too excited with that being a tool for interpretability. And then we have a big debate whether heat maps like these are causal explanations of what the model is doing. So we had a canonical paper called Attention is Not Explanation. Then we had a paper Attention is Not Explanation. And then it just continued. There is a survey paper I can share later on the whole debate. Here I just linked a lecture from my interpretability course if you're interested. So it is a tool for interpretability, but don't confuse causality with it, is what I want to say. And you know how I keep saying softmax have been used for the first time in this course to define logistic regression, multi-class logistic regression. But then I said, like, it's a tool you can use for many things. And you have noticed every time I want to squash something to 0 to 1, we just pull softmax, right? Similarly, attention is also a general deep learning technique. So a more general definition of attention will be to say that you have a set of vector values. These are our source hidden representations. And you have some vector query. And your goal is to understand, and you use attention to do that, to compute a weighted sum of values dependent on the query, right? Like, how can you give weights to these values, combine them relative to their importances to the query vector? Or we can say that query attends to the values, because we have this idea of, like, it was clearer in visualizations, those arrows pointing from decoder step to the hidden representation in the source. So in our sequence-to-sequence encoder and decoder architecture, each decoder hidden state is a query, and it attends to all the encoder hidden states, which are the values. Some kind of way people will express in machine learning to kind of, talk about all of this will be that the weighted sum, this one, CJ, that's how I called it, is a selective summary of the information that's contained in these values. So when I said, like, a kind of locality, right? Like, what's important for in the source for a given decoder step. And the query, which is our decoder step, determines which values to focus on. People will also say attention is a way to obtain a fixed representation of an arbitrary set of representation, namely the values, depending on some other representation, the query. So these are all the ways people will use, attention, or like introduce it for their own problem. So if anytime you feel like, oh, I have a set of some vectors and I have a query vector, and I kind of want to make a representation of all those vectors based on how important they are to this query vector, you can think of attention and use this procedure to get that representation. Okay, I'm going to stop here. Attention is going to become massively important when we start to talk about the transformer architecture, our go-to architecture. I don't mean I'm going to stop here, lecture is done. I'm going to stop here with the attention. So it's going to be massively important for our self-attention mechanism. So next time we have a lecture after the fall break, I will introduce tokenization that has been introduced for neural machine translation in 2016. So we are going to finally leave behind our silly white space tokenizer. And then we are going to jump into the transformer where this is going to be this encoder, decoder, sequence to sequence attention business is all going to come together. Okay, let's take a little break and then we are going to talk about midterm. Okay, so I will go over the logistics that I sent in the announcement just to be sure we are all on the same page here. And then I will see whether you have immediately some questions. I would love to kind of focus on answering those, but if not, we're just gonna chat about what we have learned so far in the course. So First of all, everyone is gonna come here, both the undergrads and grads. So if you're a grad student, please pay attention now. Do not come to the math department like you did for the practicums. You're all gonna be here. That can cause problem if you're there and then you need to come here, you're gonna waste some time. So everyone comes here. Our standard class time, starting at 1:25, we're gonna wrap at 5. All the questions are going to be multiple choice questions, which is great. It's easier, right? Some of them are going to be a little bit more complicated than others because they might have more than one answer choice being correct. I won't tell you which ones, so these tend to be a little bit more hard to reason. I did give you examples of 2 questions that had appeared previously in a midterm. So you can kind of see what kind of questions I'm thinking here. Some will be more straightforward, like that question, what evaluation method we use to evaluate language models. That's, in my opinion, pretty straightforward. The other one required a little bit of reason, right? Like, okay, I know what stemming is, how does stemming influences the vocabulary size, right? It's not super one shot. So there will be questions like that, which are more like multiple reasoning questions. I often get asked how to prepare. There is really nothing else for you to do than the review lectures. So go over the slides. I would recommend going over them and seeing whether things are familiar, whether you know what they are. Consult the recording if something feels unfamiliar. Please ask us questions in Piazza and come to the office hours if there is anything unclear. You should, as always, bring your ID with your photo. We will be checking that. And I said you can bring one side of a piece of paper. So this is a side, right? So only one side of a piece of a paper. You can bring it with some notes. My idea here is that I don't want to penalize you just because you simply forgot something that's trickier to remember. So for example, I gave an example of if in temperature scaling, we divide the softmax numerator and every summand in the denominator by T. And now does lower or higher T sharpen or flatten the distribution is a detail that can be hard to remember. And I would personally write it down on a piece of paper. So the idea isn't that you like write every single thing that you can then have it handy and retrieve it on the exam. Rather, as you're learning, you should have a sense of what's difficult to remember for you personally. That means you can't share notes because it shouldn't be the case that you have exactly the same thing hard to remember as your peer. You can digitally produce them. I know some of you take notes and write on iPad. You can put a whole slide if you want. That's okay. I did restrict the size of the font because sometimes people bring the font 6 with no spaces. That's not the point. The point isn't that you make the best notes for the exam. Rather, the point is that while you are reviewing, you can record what you have hard time with them. Okay. Are there any questions about that? So yeah, just don't bring 2 sides because then I have no idea what they're going to do about that. Because if I'm giving you only 1 side and it came with like 2 sides and they're on the same piece of paper, that's going to be a problem. Or I will take you half of your notes and we'll choose which one, which is also seems like a tricky choice. So yeah, pay attention to that. Any question about logistics? Yes, please.
Is the final cumulative?
What do you mean?
Is the final exam cumulative?
I don't want to know what you mean by that.
Does it cover the material from for the midterm or only half of it?
Just before the midterm, how could it cover?
Oh, the final exam.
Oh, final exam.
Yes.
Sorry, I thought you were asking about midterm. We'll see when the final exam comes.
Okay.
Yeah.
Do you know if we would be able to use the same note? If it was cumulative, could we use the same note sheet?
Sure. Yeah, but there will be a second part of the course, so if you want to maximize the space for the first one, then I don't see how that's gonna.
It would be only a single sided.
Yeah. Yeah.
For the questions where there could be more than one answer, at least more than one, right? Or more than zero. So there could be a question with zero right answers.
There won't be those with zero. Yeah, so it's gonna be one or more. Yeah, but I won't tell you how many, and one, it could be only one. Yeah.
There's no partial credit for showing your work, right?
No.
Remind me how the multiple correct answer, multiple choice questions are being graded. Is it like you get partial credit if you get one of the answers, or is it all or nothing? You have to get all of the answers.
You don't need to get to all the answers. So let's say there are mostly going to be four answer options. So A, B, C, D. And each one of the answer option is either correct or wrong given the question, right? If you make the right decision, you'll get, so I'm going to say here correct decision, meaning you have selected the answer options when you should, or you did not select it when it was a wrong option, you get 0.25. And you can get so for every single one of these options, which means that if you do make all the right decisions, you will get one for the entire question. But let's say you miss this one, like you said, oh, this one is correct, but it was actually wrong. You will get 0.75. Okay.
Okay.
Yeah. So basically, I'm grading each answer option and then something, however you got on each one. Yeah. Okay. Yeah.
So if we get a correct answer to get penalized for that.
You get penalized in a sense you get 0 where you could get 0.5. 0.25, what did I say?
So for example, if the multiple choices they only choose correct answer and they select all of the answers. So it's been
Sure, you can risk it. You know, I'm not telling you how much they're gonna be, like what's their distribution gonna be. So if you just do random decisions, you could be lucky and get some points. I wouldn't recommend it.
Because there are two correct answers and select all for now. I also have two correct answers for what questions.
You are assuming there are two correct answers. I will not tell you whether correct answer. So you can just assume that on average there are two correct and make that decision and get half of the points for every question. I can tell you that there won't always be two correct answers. So then you are risking, you know, your strategy. So try to do, you know, try to select those that you think are correct. Yeah.
Yeah, it's the same as having four true or false questions graded at the court.
I think you get the general vibe I'm going here. So let's, you know, wait for the rest of the questions when it comes to exam. Now you are picking me like little bits and pieces of the exam.
How many questions are these?
You're gonna see. I'll give it away almost.
17 for
Okay. Yeah.
And we'll start and she will be.
Yeah. You don't need to stay, but just when you give your exam back, the solo one, you're going to give your points as well. Yeah. You need to print calculator. No. No reason for a button. No digital devices necessary whatsoever. Okay, I feel like our anxiety is just growing as we ask more questions. I think in grand scheme of things, most of you are either senior undergrads or grads. This is a very easy exam format, to be honest. Like it's just, you know, multiple check questions. I'm not asking you to derive math. I'm not asking you to write code. I'm not asking you to reason about math or code. You know, like you do need to understand the concepts you have learned about in this course, but from my experience, if you have been coming to these lectures, you're already in a good spot. You kind of have a sense of what I'm emphasizing, what seems important to me. I would also remember that, you know, while going over the materials. So I think you're already in a pretty good shape. That said, go over the materials just because you might have forgotten about something. You know, it's been a few weeks since we started. Okay. We have 10 minutes left. Are there any questions related to the course? I know there was one question I wanted to cover from Piazza, which was when do we use unknown token? And we are going to use unknown token whenever we are in a situation where we can observe a token at the test time that we haven't seen during the training time, which is so far in this course that can always happen. We didn't have a tokenizer that enables us to never not see unknown tokens. So the answer to that question is, with every single model that we have learned in this course, we can encounter a token, namely a word, because we have been using word white space tokenizer. We can observe new words during the test time. And this means for everything we have learned so far, you would add that special unknown token to your vocabulary, assign it some embedding, like 0 maybe embedding, or something random embedding if you have save the 0 embedding for the attached token, but this can always happen. But maybe as a little, to give a little bit of excitement about what comes next, once we learn about a little bit smarter tokenizers, this will become a thing that never happens. So that's good, and I hope it keeps you excited for the subword tokenization. Other questions? Yeah.
Does it include today's lecture also, so today's attention?
Yeah, it's precious in your mind. Should be the easiest one, right? Yeah.
When it comes to word embedding matrices and how we're applying them in the engineers, like what is the general idea of like the word embedding lookup? Right, we're taking a full row.
Yeah.
Okay.
Yeah, exactly. So when our first layer is going to be embedding layer of the shape, number of rows will equal number of tokens in the vocab, and number of columns is the size of the embeddings, because we basically started them row-wise in an order they're indexed in the vocab, right? Which was also why I asked you all those questions in the practicum about like how would you construct it. I basically was probing them to understand what I just said. Yeah, let's see later. Yeah.
We'll talk a little bit, what teacher forcing is.
Yeah, teacher forcing. I do feel like that's a little bit hard to wrap one's mind around. So, okay. When we started to talk about generator models, right, we have said that we are going to produce next token, and it started from that special beginning of sequence token. And then we have done some sequence of operations, right? We have produced a hidden representation of that special token. And then when we have finalized transforming it, we have produced logits, we have applied softmax to them, and then we got the probability distribution over the vocab, right? And then we could have sampled a word. So here, let me just write. We have logits, then probabilities, and then we sample. Now, during training time, and during training time only, we have an option. We could use a word that we have sampled here, right? Or we can use as a word, next word that's going to appear in the input, a word that actually appears as the next word in our data, right? So I'm going to say word predicted. And here I'm gonna write word and I'm going to call it goal or ground truth. So I have options between these two words as my input here. So if I put W gold here, basically I ignore that this is the most likely word under my model here. I'm rather introducing the word that had actually appeared as the next word during training only. That's called teacher force, because teacher, in a sense, that this is true, this is a correct information, and you are forcing that correct information. So during training, we have options between W predict versus W gold as the input, as the next input, I would say. That's called teacher forcing when we use W gold. Yeah, of course.
I think the part where I'm maybe having a hard time because I understand the difference between using the predicted word versus the actual one.
Mm-hmm.
When we're training, our goal ultimately, right, is to train the model so that W predicted will be the goal, right?
Yeah.
And so the way we're doing our training is that we'll compute our loss based on beginning of speech to the predicted word, right? And then the next time we'll have beginning of speech first word, and then we're trying to compute the loss function based on whatever the second word is, right?
Okay, let me try to say what the loss function is, and then I might clarify what's going on. Okay, so at every decoding step, we know what the true next token is, right? And we are always in this course have used negative log likelihood as our loss, right? So we are going to have negative something, negative log, and negative probability. So here, the probability we are going to use is the probability of seeing W gold given BOS. Right? So that's the probability. So in our softmax vector, we have index for the gold word, which might be 2, right? And we take that value as the probability logarithm negate. The predicted one can be like 5, right? That's its index, and then that's the probability for the predicted one. We wouldn't use it here. We are going to do this at every decoding step, and then we are going to average these losses, and then vector propagate. So here on the next one, I'm going to say W1 gold, okay? Next loss is going to be negative log probability of W2 gold BOS. And then here depends what I put in the input. This can be either I place W1 gold or W1 predicted. Okay, right, like that's what got in the input, and that's why we got this loss again. So let's say here I did teacher forcing. This would be based on this information. What's this probability, right? If I have not done teacher forcing, this would be W1 predicted, and here I would have W1 predicted. Is this now clearer?
That makes so much sense. Thank you.
Okay, great.
What sort of impact do we see when we do teacher forcing? Maybe it's that we're using this gold label or this, this gold word as opposed to the predicted word.
Yeah, so initially, when we didn't do pre-training that we're going to talk in the next part of the course, all of our weights are randomly initialized weights. So our model initially is honestly rubbish, right? It has no idea what to do. So these W1 predicted, I get in the initial part of my training, but not. It will be gibberish. So how can you learn if I add in my input gibberish, how can I learn what the next word is? It's like setting up your whole model for training, right? Okay. So if you're starting with random initialized weights, your model will basically behave like a random model initially. So it won't produce any good predicted values here. And then if you give those as an input, you just don't have a chance to learn, right? Does this make sense?
So teacher forcing is good if we're starting with
Random weights.
Random weights, but I take it it's going to not be as necessary once we have pre-training and we have set weights initially.
It's not gonna be important for quality of training, but during training, it's gonna massively improve the speed of training.
Okay.
And this is the reason why. So if I do not use teacher forcing, I simply must sample this word to be able to add it here, right? Like I have to first sample it to be able to use it, right? So that means I need to do this prediction sequentially and build my input sequentially to be able to produce the representations. Whereas with teacher forcing, because I know what the input is gonna be, right? It's gonna be the actual observed sequence of the data. I can immediately construct that sequence. I can do all the hidden representations using batch multiplications, right? So if I had batch time sequence length, right? This is the sequence length of these things, time dimensionality, that's my initial tensor. And I don't need to now sequentially do anything. I can immediately use tensor operations, which are massively faster, what GPUs are designed for. And I can immediately get all of these losses. So that's super fast relative to doing this sequentially.
So can we skip the sample step of that pipeline that I see here by doing teacher forcing?
Yeah.
Do we also skip the probs step as well, or do we still have to calculate the probabilities of the next token?
So if we are training, this is what we're talking about. We are training. We need a loss, right? This is the loss, right?
Okay.
Where do these probabilities come from?
They come from the probs.
Probs, right? So you can't skip that.
But we can skip the sample step.
You can skip sampling.
Okay.
Yeah, and sequentially construct the input.
Got it.
Of course, the downside is that diversity of your outputs are now determined by what's in the gold data. And we might be posing when we come to the inference time. And this is crucial that you remember. Teacher forcing is only an option during training. You can't use gold data during the test time. So it is crucial to realize that there's no teacher forcing. And this is why teacher forcing can be problematic. If at the test time you cannot use teacher forcing, the type of text your model produces can be different of the data that is observed. And now basically you create what we call out of domain or out of distribution example, where your generalization capacities of your model can struggle. Just because it hasn't seen exactly that type of text before. That's why we have introduced schedule sampling during the training, where with some probability later in the training, we are going to use outputs of the model itself rather than teacher forcing. But yeah, speed is a huge thing. So teacher forcing is definitely going to be used a lot during training. And by a lot, I mean almost exclusive forcing, because models are going to become better and you're just going to need that speed. Okay, so yeah, I will just quickly go over like 1 minute overview. Like in this course so far, we have talked about discriminative and generative machine learning for text classification and text generation, right? Everything started with some preprocessing steps, like lowercasing your words, for example, and then we always tokenize our text. There is never in this course we talked about working with row sequences ever. That's not gonna be possible. We have used a crappy tokenizer, white space tokenizer. We will throw it away as soon as we can. And then we learn two feature representations. And remember that we need to represent text with numbers and actually a lot of numbers to capture their features of the text that then the model can correlate with whatever output we are pairing that to. So we had bag of n-grams and we had word embeddings. They differed quite a bit. Remember that contrast I was giving you when I was polling you about like, are these dense? Are these sparse? Don't forget about that part. And then we have created for classification, logistic regression and feed-forward neural network. For generation, we have talked about counting frequencies and feed-forward neural network for language modeling and recurrent neural network for language modeling. And now today we also have the embedded attention. And then it's really important that you always remember what your evaluation metric is. So you don't want to embarrass later in your life by saying, oh, I'm going to evaluate classification and perplexity, or I'm going to evaluate language modeling with F1 score, right? So you need to remember what is the defining metric that you should be reporting. For classification, that was accuracy, and F1 score for language modeling, that was perplexity. And we also had evaluation of word vector models. So we had intrinsic evaluation being correlation of vector similarity with human judgments of word similarity. And our extrinsic evaluation was if I add these learned embeddings as the embedding layer for my, let's say, classification model, does my model have better performance relative to some baseline, right? So that's called extrinsic evaluation. And another super important bit is to remember when we are doing sampling, all the options we had. We had greedy, beam search, temperature scaling, dot K, and nucleus sampling. All of them are important and going to become really handy when we move forward with the course. Okay, good luck. Don't stress too much. It's going to be okay.